All right, so as we're going to start our look at the binomial theorem to review what you've done in the past, I want to first of all make sure that we understand what we're talking about first, okay? We're talking about expanding or multiplying out some binomial raised to a power, all right? So instead of doing, x plus y times x plus y times x plus y times x plus y times x plus y, and doing a whole bunch of multiplication, there's actually a pattern to it. Okay? There's a pattern to it. And within the pattern, there are a number of smaller patterns here. And I want to see if you guys can pick out these patterns, because really that's what mathematics is all about, is patterns and recognizing those patterns and how they work together. Okay? If you can recognize the patterns here, then when you actually see the theorem looks a lot harder than it is. Okay? So, what patterns do you see in this answer? Or
1, 5, 10, 10, 5, 1.
Oh, okay, so you're looking at these coefficients, right? 1, 5, 10, 10, 5, 1. We see some symmetry in those,
5,
right?
3, 4, 5, 4, 3, 2, 1, 0. X to the power.
Very good. The x power, the x's have powers that go 5, 4, 3, 2, 1, and 0.
And 0, 1, 2.
Excellent one. Good. So the y's there are no y's in the first term, and then we have y to the first, y squared, y cubed, y to the fourth, and y to the fifth. Okay? Good, good. What else do you notice here?
Wait, here's. Oh, yeah, okay, never mind.
He said they all add up to 5, right?
Yeah.
We didn't mention that yet, but yeah, the exponents for each term will always add up to the power that you were raising it to, 5. Okay? What do you?
I kind of have, because I remember like last year it's kind of the term is added by the total above it.
You're talking about Pascal's triangle.
Is this one? No.
This is actually the 1, 5, 10, 10, 5, 1 is one of the rows. It's the
Yes.
5th row in Pascal's triangle. Yeah. So, and we'll see that. We'll see that. Okay? Good. There's one other thing I want you guys to notice. It's not necessarily a pattern within one of them, but as you look at all of the different expansions, you'll see it as a pattern. How many terms did we end up with? 6.
One more.
It's always one more than the power you're raising it to, okay? So if you're raising it to the 5th power, you're going to have 6 terms. Okay? So great. We've got a lot of good patterns that we see in here, and those are going to be important to recognize as you're doing various problems. Okay? So, let's take a quick look at the proof itself, or the theorem itself. We're not going to prove it. Honestly, I don't remember how to prove it, so we're going to look at this. Okay? The expansion of x plus y to the n. Now, this could be anything, this x. It could be a 2x, it could be a 3x squared, it could be a 4b. It doesn't matter. Whatever comes first in the binomial, and then whatever comes second in the binomial would be our y. Okay? Mm-hmm.
What if you have a subtraction instead of addition subtraction?
If you have subtraction, you would treat it as though it were x plus a negative y to the n. So you would just keep that negative with that second term. Okay, good question. All right. So you see this theorem here, x plus y to the n equals x to the n plus n times x to the n minus 1 times y, and so on. It looks really complicated. But the fact of the matter is, if you keep in mind the patterns we just saw, it's not complicated at all. All right? One thing you should be aware of, however, is this term right here in the theorem gives us the general term for any one. It's the form for any one of our terms. Even these ones where here it just says y to the n, we could see that as n choose n, x to the n minus n, y to the n. All right, obviously that would be x to the 0 power, which is 1, and n choose n is 1, so that's why it only ends up being y to the n. But all of the terms fall into that same general pattern here. Okay? And you can see a couple of the patterns we already saw here. Notice the exponent n minus r and the exponent r. If you add those together, what do you get? N. Just like we were supposed to. N minus r plus r is just n. Okay? Now, the other thing here is, remember the powers of r that we just saw. Okay? The powers, or not the powers of r, the powers of y. Y started at the 0 power, right? We didn't have any y's. Then we had 1, then 2, then 3, then 4, all the way up to whatever n is. Okay? So think with me here. If y ends up being to the 4th power, let's say, which term in the expansion is that going to be?
The last one. Well, oh, for this one?
For any. If it's the 4th term in the... I'm sorry, if y is to the 4th power... What?
Fifth term, right?
It would be our 5th term, okay? It would be our 5th term because you start counting with y equals y to the 0 power is our 1st term. Y to the 1st power is our 2nd term, okay? So the term number will always be r plus 1. Okay? Whatever the power of y is, that second part, plus 1. Okay? So that's going to be incredibly important when we get to our unit, our second unit, where we look at probabilities. And we're going to use this theorem here to help us figure out probabilities in certain situations. And that's really cool, okay? But in order to do it, you have to be able to pick out one specific term out of your expansion, because you don't want to have to do the whole thing. All right, so we can figure out what term we're working with. Then we have the coefficient. We saw the 1, 5, 10, 10, 5, 1 on the example we started with. Those numbers all come from this combination. N is the power we're raising the expansion to. R, we just said, is the power of y. Okay? So, I gave you some examples here. We briefly looked at the combination earlier in this unit, and I mentioned this notation also meant the same thing. Okay? So I gave you some examples here, and I want to kind of answer 3 questions related to each of these examples. All right, first of all, if we have an 8 choose 8, what power was x plus y raised to?
0.
No?
Oh, raised to is 8.
It's 8, okay? Notice here, n is the top number, and n is the power you're raising your expansion to, right? So, oops, too much. Let's try it one last time. There we go. All right, so this must be to the 8th power, because this is an 8. Okay? Now, if I'm doing 8 choose 8, which term is that the coefficient for?
Ninth.
It would be our, what'd you say?
Ninth, I think?
The ninth.
Yeah.
Okay. Remember, we start counting at 8 choose 0. We go all the way up to 8 choose 8. That's 9 terms. R is 8. So here's the term number. Okay. The term number is R plus 1. So if R is 8, then 8 plus 1 would give us the ninth power. Or the ninth term. Okay? Now, what does it equal? You can use the formula for the combination, all right? Or,
Y to B.
this is going to be, if we're raising it to the 8th power and it's the 9th term, it's going to be our last term, right? You guys were already talking about Pascal's triangle. You remember what the first and last number always were? 1. All right? So if you got the first term or the last term, you don't have to work out the whole combination. You know it's going to equal 1. Okay? And if you think about it logically, remember what the combination gave us. Choosing R items out of N. How many ways can you pick all 8 of 8 items? There's only one way you can pick everything, right? So, there we go.
What if x or y has a constant before, or like maybe it's 3x or 3y? Would that change the? What do you?
It'll change the number you end up seeing, but this combination is just talking about the binomial coefficient by definition. All right, you're right. If we were raising like 2x plus 3 to the 5th, one of those, we would have 2x to the 5th power. The binomial coefficient would be a 1, but you're right, 2 would be raised to the 5th power. We'd end up seeing a 32 in there, but this is what we're talking about here.
So it is a coefficient, right? What does it equal?
What does it equal? 1. 8 choose 8 equals 1. Okay. Now let's talk about 7 choose 0. This would be one of the coefficients for x plus y to what power?
7.
The 7th. Okay? It'd be to the 7th power, because n is 7. Which term does this go with? The first. R is 0, right? Because it's 7 choose 0. So this would be the first term. And what does it equal?
1.
It equals 1. That's right. Okay? It equals 1. Remember the Pascal's triangle always starts and ends with 1. Okay? Alright. We're going to get ones that don't equal 1 eventually here. So let's look at one of those. Okay? If we have 8 choose 2, that's going to be a coefficient for x plus y to what power? 8th. Okay? Put the cell phones away. Okay. It's x plus y to the 8th power. Again, n is this number here. Alright? What term does this go to?
30.
The third. Good. R is 2, so this is the third term.
Question so far.
Mhm.
What's that R is?
I'm sorry, what?
R. What's that means?
I can't hear what you're saying. Sorry.
I don't understand
R?
Yeah.
R is always the number you're choosing. See this? The number you're choosing, okay? Or in this notation, it's the number that comes after the C. So here, 8 is N, 2 is R. Okay? And, by the way, I know that this term, since 2 is r, I know this term is going to have a y squared in it. Because remember we said the r is also the power of y. Okay?
So R is always the power of your second term.
Yes, r will always be the power of that second term. Okay? Now, what does this equal?
28.
Okay? Let's work through this. So we're going to use the formula up here. Alright, so it's 8. We just said n is 8. And then we have n minus r, so 8 minus 2 times r factorial. Okay? So we have 8 factorial over 6 factorial times 2 factorial. How do we simplify this? Good, get rid of the 6 factorial. And what's left on top though?
7 and 8.
Good, 7 times 8, because you count down. 8 times 7 times 6 times 5 times 4. But the 6 and on down cancels with the 6 factorial. Good. So 8 times 7 is 56. What's 2 factorial?
28.
It's 2, so good. Yeah, it'll equal 28. Okay?
We're oh no, okay.
Alright, our last one here, 10. Choose 3. This would be for the expansion of x plus y to what power?
10.
The 10th? What term are we working with?
4.
The 4th? And someone tell me how we would figure out what this equals.
Okay.
10.
Someone,
10.
wait, how did you get that?
I put 10. I used the formula.
Okay, yeah, but tell us what you plugged in. So you had the 10 on the top, 10 factorial.
And 10 minus 3
Good.
multiplied 2.
Multiplied by 3 factorial. Okay.
90.
So that's 10 factorial over 7 factorial, 3 factorial, right?
Cross out 10 and 7.
So what did you do at this point?
Let's try it.
The 7
What's his name? John?
Hang on, shh, quiet please. What?
the factorial over 7 is we use the 10 and we only have 10 multiply 9 and 8.
Okay, very good. 10 times 9 times 8. And the 3 factorial is equal to 6, right?
Yeah.
So you can then multiply that. That would be 720 divided by 6, which would be 120. Okay? So that's how you can work with those, alright? That's kind of the most important thing to make sure that we get right. The rest of it's all patterns.
What does this all define though? This is all define the expanding this out, I guess.
Initially just the expansion, later on we'll apply it to probabilities.
Okay.
So. Alright, so on this example you'll notice that instead of just an x and a y, we actually have a 3x and a minus 2. Okay? So notice that you could kind of think of this as 3x plus a negative 2, okay? And the key thing is here, whether you're talking about them as x and y or a and b, it doesn't really matter. But those are the terms that are being added together, okay? So you start with this first term at the highest power. Okay? So I'm going to start with something to the 6th power. What do I have to the 6th power in this case? It's a 3x, all right? And here's where parentheses are important. It's going to be 3x. It's not just x to the 6th power. You're going to raise the entire term, 3x to the 6th power. All right? Does that make sense? Kinda? All right? Now, what I would recommend is leave yourself some space. I know I'm going to need 7 terms. Okay? So there's one term. There's going to be my second term. My second term is going to have 3x to what power? Good, to the 5th power. I'll leave a little bit of space. This term is going to have a what?
3x to the 4th.
Yep, 3x to the 4th. And so on. Remember, we're just counting down. This term will have 3x to the 3rd. This term will have a 3x squared. And then this term will have a 3x to the 1st. And then my final term isn't going to have a 3x at all. Okay? Does that make sense?
Yes.
Okay. Are there any questions about that part? Because right now we're a third of the way done with this expansion. Okay? What's the second term in our binomial? A -2. Be careful with the negative. Okay? It's a -2. So, how many -2's is my first term going to have?
0.
0, right? And then this term is going to have -2 to the first. This term will have -2 to the second. -2 to the third. -2 to the fourth. -2 to the fifth. And then finally, a -2 to the sixth. Okay? You seeing how we're doing the pattern? Remember the first term, the 3x, you start at the highest power and you count down till you get to 0. The second term in the binomial, you start with none of them and then count up. -2 to the first, second, third, fourth, fifth, and finally the 6th power. So at this point, all we have to do is figure out our coefficients. Okay? Need to figure out our coefficients. And this is where this n choose r comes into play. Alright? Now we're going to have a different one for each term. But you can save yourself a little bit of time. Alright? What are the first and last coefficients always going to be?
6.
No? 1. Alright? They're always going to be 1. Okay? The second one and the next to last one are always going to be n. Okay? Now let's see why that is. In this case, what is n?
6.
N is 6. Very good. So we have a 6 choose something. Now, the first one was 6 choose 0. That's why it equaled 1. There's only one way to pick nothing out of a group. Okay? Just like the last one is 6 choose 6. There's only one way to pick everything out of a group. Alright? So in this case, if we do 6 choose 1, let me ask you something. How many different ways can you pick one thing out of 6?
6.
6. Alright? You can either pick that one, or 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 that one. Okay? So what does 6 choose 1 equal? 6. Alright? So there's our coefficient. And guys, that's why on all of these, the second term is going to be n. The coefficient's going to be n. And also the next to last term, because think of it this way. This next to the last term is 6 choose, how many? 5. Okay, 6 choose 5. Now think about it this way. If I'm picking 5 people out of 6, in essence I'm just picking 1 to leave out, right? So these are going to give me the same values. Whether I'm picking 1 out of 6 to include, or 1 out of 6 to leave out, I'm going to get the same number of possibilities. Alright? So what's my coefficient for 6 choose 5? It's 6. Okay? Are you guys following this? Is anyone confused or have a question? Okay? So, here's where we actually get into stuff we can't just do logically. Alright? Once we get past the first and second on either end, then we need to start actually calculating. So let's do that here. Okay? So for this coefficient here, it's going to be 6 choose what?
2.
Okay, why 2?
What's the third term? But it has the second. Y is to the second degree.
Okay, good. Remember, it's n choose r, right? And r is always the exponent of that second term. Okay? Well, here, r is going to be 2. Okay? So 6 choose 2, and now we're using our formula. Our formula, remember, is n factorial over n minus r factorial times r factorial. And now you just got to simplify. This is why we practiced simplifying stuff with factorials earlier. Question?
Could we just use Pascal's triangle?
We can eventually to, especially with a lower power like this of 6, it wouldn't be too hard to get there. One reason why I want you to learn how to get it this way is just so that, if it were to the 20th, or which we will run into when we get into probabilities in the next unit. Okay, we're going to use this theorem to do probabilities. So we'll need to be able to do it with this. But you're right, if you can use Pascal's triangle, it's certainly easier. Okay. So here we have, how are we simplifying this one? Okay, subtract the 6 and the 2, so 4 factorial, 2 factorial.
And then it's on the bottom. Or do you want to?
You do 30 over
Yeah.
2.
Okay,
2, 1.
good. So the 6 factorial, if we take the 6 and the 5, we can cancel the rest of it with the 4 factorial, right?
Yeah.
So it's 6 times 5 times 4 factorial, we could rewrite it as. And by the way, what's 2 factorial equal? 2. Alright, so I'll just write that as a 2. Okay, so those cancel out. And then I have 30 over 2, which is 15. Good. Alright, so now I know that the coefficient here is 15. And by the way, what did we recognize as a pattern for our coefficients? They were... There was a 1 on either end, then an n on either end, and...
Oh, then the 2 middle things are the same.
Okay, there was symmetry, right? So, if this one is 15, that means this one over here is 15. Okay? because that's going to equal the same thing as 6 choose 4. And you might be like, well, why does, well, not 6. You might say, well, why does 6 choose 4 equal the same thing as 6 choose 2? Well, think about it. If we're picking 2 to include, over here when we're picking 4, that's the same thing as picking 2 to leave out, right? You know, so these are logically the same thing. 6 choose 2 and 6 choose 4. And mathematically they end up being the same as well, because if you do 6 minus 4, you'll get the 2 factorial, and then r is 4, so you'd have the 4 factorial in the denominator. Okay? So there's really only one more combination we need to do here, and that is for this middle term. Okay? What's the combination we need to figure out?
6 choose 3.
Very good. 6 choose 3. Alright? Take a moment here and try to figure that one out on your own.
16.
No, not quite. Did someone else? What? 20. Good, me. Alright. 6 factorial over 6 minus 3 is 3 factorial times the r factorial is 3 factorial. So you have 6 times 5 times 4 times 3 factorial over 3 times 2 times 1 times the other 3 factorial. Okay, so you'll notice here the 3 factorials cancel, and this whole thing down here is 6, so that'll cancel out that 6, and we're left with just 20. Okay, so good. So our coefficient here would be 20. Okay? Yes?
You don't have to actually do like 3x to the 6th power. You don't actually have to solve that.
No, yeah, you do. Okay? We've done the hard part. Now all we have to do is simplify. Okay? Are there any questions as to how we got up to this point? Because yes, you should simplify here. We'll make it green. There we go. Okay, so now this is the part that's not hard, but you got to be careful about. Okay, so you got to do 3 to the 6th. All right, 3, 6, 7, 20, 723? 729. Okay, so yeah, now we have our whole answer here. But we've got to simplify, okay, 729x to the 6th. And now, notice here we have this negative. We have a negative to the first power, then a negative to the second power, then a negative to the third power, then a negative to the fourth power. What's going to happen to our terms? Yeah, they're going to alternate positive, negative, positive, negative. If you just pay attention to that, this next term is going to be negative. That kind of makes it easier to simplify because you don't have to like think about, you know, the negative as you're figuring out what the number is. All right, so here we have 6. I know it's going to be an x to the 5th. Why isn't that working nicer? Okay, I know it's going to be an x to the 5th. We got to do 3 to the 5th is 243. Okay. Let's let's see, 14, 58, 28, 29, 18. Is it 2918? Is that right?
I got
2916 you got?
yeah, 20.
Okay, I'm doing it in my head. You guys have the calculators, so double check me. All right, so we have 2916 x to the 5th. So then the next one, 3 to the 4th. Negative 2 is squared, so I know it's going to be plus. Yes.
So what you find from 6 choose to, or like whatever, like throughout the whole thing, is you multiply it by all of that.
Any numbers, yeah, any numbers that happen to be in the term, you're going to multiply that.
So it'd be like 3x is like times negative 2 times 6.
Yes, yes. That's your whole term of the expansion.
Okay.
And that's the thing. We call those combinations the binomial coefficients. They're not necessarily going to be the coefficient you end up seeing in your final answer. Like in this case, I mean, the binomial coefficient was 1, we've got 729. And then the binomial coefficient was 6, but we end up seeing a negative 2916. Okay? But that's because our terms in our expansion also had numbers. Alright? So let's see what the rest of this is going to be. It's going to be positive 30 times 81, 243, 2430, x to the 4th. I think that's right.
I got.
Are others of you getting that?
I got something different.
Yeah, I did too.
I got 4860.
Yeah, I got 48.
4860?
Yeah.
Oh, I only doubled it, that's why. I lost a 2. Thanks.
Please never make us do this on a test.
No.
Oh my god, it's so long.
You have a calculator.
I mean, like, we learned last
It does all the tedious stuff for you. All right. So then the next term is going to be what? Positive or negative? Negative. So we have 8 times 3 cubed is 27 times 20. What does that give us?
432.
Okay. And that's x cubed. And then plus, you have a 15 times 9 times 16. Oh. Okay. And then the next one's going to be minus. What is it again? And that's just x. And then
64.
plus 64. Okay? So, this whole thing is our answer. And believe it or not, that still will be faster than foiling everything out. Okay? So. And as you guys get the hang of it and you see the patterns even more, it'll be even faster. Okay?
But if we had a number like 6, could we just use Pascal's triangle?
Yes, and that's actually what I want to look at here in a sec. Are there any questions about this expansion though? Anyone not getting it to work out or not sure how we got a certain piece of that?
Wait, hold on. Actually, wait. So why do you use factorials?
The factorials are for the actual coefficients, the 1, 6, 15, 20, 15, 6, and 1. Remember we saw the symmetry?
Yeah.
To get those actual numbers, that's what we're doing, or that's when we're using these combinations. Okay? Remember up here, the binomial theorem says that each term has this coefficient, n choose r. Alright? And remember the formula for n choose r is n factorial over n minus r factorial times r factorial. So that's where the factorials are coming from. Okay?
Okay.
You should be familiar with using those, although, as we've mentioned here, there is something called Pascal's triangle
Yeah.
that will enable us to find them faster sometimes. As long as n is not too big, it'll actually be faster to use Pascal's triangle.
So
Okay?
if we had a question like this on the test and we used Pascal's triangle, it wouldn't be wrong?
No, that's fine with me.
Okay.
But you may have a question on a test where I say, hey, what's the fifth term of this expansion? You know? So that's where, okay, fifth term, that means r must equal 4. Remember, the term number is always r plus 1. Okay? So if I'm trying to find the fifth term,
6.
okay, the fifth term means that whatever the second factor is going to be raised to the 4th power. So I'm going to have a negative 2 to the 4th power. Alright, and that kind of opens up the door for everything else I've got to figure out. I know it's 6 choose something, and I'm always choosing r, but now I know r is 4. And then, what power would the 3x be raised to if the negative 2 is raised to the 4th power?
2.
It's to the 2nd, because the exponents have to add up to 6. Alright? So, one of the applications here is going to be picking out a specific term. Okay? Now notice here, that's exactly what we got down here. The 1, 2, 3, 4, 5, that's the fifth term. Okay? So, it's useful to be able to pick out individual terms. And we'll see that especially in our next unit when we're studying probabilities. Okay? Alright, any other questions? Alright, let's look at Pascal's triangle. Alright, this is really kind of a cool thing. Here's Pascal was a mathematician. This is one of the earliest calculators. He invented it's called the Pascaline. It was mechanical. It used gears and things. And it could actually do addition and subtraction, multiplication, division. I think it even did square roots, which is insane. Yeah, that's kind of a cool invention of his. Replica, obviously. But let's take a look at Pascal's triangle. Alright? You have this, we don't even really use the 0 that much. You don't even have to write that one. But notice Pascal's triangle, just dealing with the coefficients. Here's the one that we just used. Okay? The x plus y to the 6th. Notice 1, 6, 15, 20, 15, 6, and 1. Okay? So, it's the same thing we got with those combinations. If we look at just the coefficients and throw out the x's and y's, you start to see some different patterns. Okay? The first pattern, and this is really how you can construct your own Pascal's triangle, is that every term on the next row is going to be the sum of the two, it's kind of in between. Right? If you make this, if you look at it in terms of this little triangle here, 4 plus 6 is 10. Or 15 plus 6 is 21. Alright, so if I'm making my own Pascal's triangle, I can start with the 1 and 1. And notice all the rows start with 1 and end with 1. Okay, so on my next row I put a 1, but now I'm in between these two 1s. So 1 and 1 is 2. And then I'm to the end of the row, so I put down a 1. Okay? And then I put down a 1, and then notice here's a 1 and a 2, so this must be a 3. Here's a 2 and a 1, so that's a 3, and then I'm to the end of the row, so now I have a 1. Okay? So now I have a 1, 4, 6, 4, 1. Okay, a 1, and then a 5, and then a 10, another 10, a 5, and a 1. Alright, so you see how to build this yourself? Being able to do this quickly can save yourself a lot of time having to use the combinations. Alright? Now, what are some other patterns that you see in Pascal's triangle?
2, 3, 4, 5, 6, 7.
Okay, yeah, notice if I follow down the second term in each of the rows, okay, or if I look at the next to last term in each of the rows, it's the same as the power of my binomial, okay? Notice this is the first row, that's x plus y to the first, right? Down here, 6 is my second and next to the last one. That goes with an x plus y to the sixth. Okay? So if you'll know that, you can pick out what row you're supposed to use really, really easily. Just look at what n is. Okay? So, there's our Pascal's triangle. Again, being able to construct this pretty quickly will be really, really helpful. Okay? Alright, so, the remainder of our time, some of you tried some of the IP, some of you didn't, but the remainder of the time we've got here, I want you to spend working your way through some of these practice problems. Here, these ones don't have any coefficients in front of the x, so they're a little bit simpler. Okay? Here you have some that actually do have coefficients in front of the terms, so they're going to be a little bit more complex, but still it's the exact same principle that we've used on every other one.